Okay, so we were talking about the Lagrangian dual function Q, and we discussed two very interesting properties of it. One is the fact that this function is concave, and the other that this function's domain is convex. And what is unique is that no matter what function you take, whether the function is convex, non-convex, linear, non-linear, these two properties hold. And this is why duality is a very useful property. Okay. So, what is the implication? Why do we care? Implication. The take home message from here is that solving the dual problem, can you say that is always a convex optimization problem? Okay. Why? Because minus q is convex. So, remember in constraint optimization, how do I define a convex optimization problem? What were the two criteria? Function is convex and the constraint set is a convex set. Both of these are needed. So, this is a place where you have to be careful. If your function is convex but your constraints give a feasible region which is not convex, then this problem is not a convex optimization problem. Okay, so be careful of this one small catch. Okay, so now let's prove these statements. They are actually very simple to prove. Okay, so no big tricks involved over here. The first thing that we have to prove is Q is concave. Right. So we can basically go back to our very simple definitions of convex functions, right? So supposing let's take lambda is the parameter here. There are 2 points over here. And I have drawn 3 possible functions over here. Okay. So which is a convex function among these 3? Black, blue, orange. Right. So strictly speaking, orange also because it's the equality, right? So this is our convex, and then this is our concave, right? So how would I define a concave function? So let's say this is lambda 1, lambda 2. So what would be the definition of a concave function? It's just analogous to convex, but what is the difference? Correct. So in words, the function value lies above the line joining the 2 points, right? So it would be something like, so if I take q of alpha 1 lambda 1 plus 1 minus 1 minus alpha. Why is there a 1 here? Just alpha lambda. This should be greater than or equal to q of alpha times q of lambda 1 plus 1 minus alpha q of lambda 2, right? And is there any slight something that we are missing? Is there a range on alpha? Right? Alpha belongs to 0 to 1. Okay, this is the definition of a concave function. Okay, and this is what we have. So we have to prove this. Okay. So remember the definition of the Lagrangian is what? L of x comma lambda is f of x minus lambda c of x, right? This is how I define the Lagrangian, right? And how was Q defined? I minimize this with respect to x, right? Okay, so with these two definitions in mind, I have to work on proving this concavity idea. Okay. So let's take one big Lagrangian, right? So let's take Lagrangian. What is the parameter that I should be focusing on, x or lambda? lambda, right? Because when we are talking about concavity of Q, we are in terms of Q of lambda. So I am interested in what happens to lambda. Anyway, x gets factored out over here because I am minimizing with respect to x. I will be left with a function in lambda. I have to prove something in the lambda domain, right? So I should take a linear or a convex combination in the lambda space. Right? So that would be something like 1 minus alpha times lambda 1 plus alpha times lambda 2. This is one big Lagrangian that I can take, right? So if I substitute this into the definition of the Lagrangian, will it split into two Lagrangians? Yes, because it's linear in lambda, it will just split up. So what will the first Lagrangian be? 1 minus alpha times x comma lambda 1, right? It's simply linear, and then this becomes alpha times Lagrangian of, right. Very good. So this is true. Now to reach the Lagrangian dual from here, what operation do I apply on both sides? I heard the correct answer. What is it? I have to minimize both sides with respect to x. That will give me the Lagrangian, right? So if I take this equation and do a minimize with respect to x, so what will become the left hand side? Q of this whole thing, 1 minus alpha lambda 1 plus alpha lambda 2, just by definition. What happens to the right hand side? Are you sure? So one answer is that this becomes 1 minus alpha into Q of lambda 1 plus alpha into Q of lambda 2. Right? So before we go that, maybe I just need to mention one thing. What is this? Min of A plus B and min of A plus min of B. What is the relation between these two? Equal, greater, less than? I hear greater, I hear less. So supposing I take A equal to x and B equal to minus x, then what will happen? The left hand side will become 0. What is? I am minimizing. Min means not, min is standing for minimize with respect to. That's a minimization operation. Correct. A and B are functions of x. So then what would you say? Which way should it go? Okay, I hear less than equal to, I hear greater than equal to. Take some, right. So it can go lower, right? Because each of these terms I can minimize separately, right? So this is actually going like this. Okay. Alright, so this is actually, so on the left hand side I have Q of this expression, and on the right hand side I don't have Q of this plus Q of that. Instead what will I have? This will become greater than or equal to. Now I can apply the minimization on each of these separately. So this would become 1 minus alpha times Q of lambda 1 plus alpha times Q of lambda 2. Okay. Actually we are done. This is what we wanted to prove. If you look back at the definition of concavity, here is the definition of concavity, right? The function graph lies above the convex combination of the function values, right? So this is Q of, right, and this, right? So this is whatever, you can see what the difference between this and this is, right? Right. So therefore we get so it's actually a very simple proof, does not involve any complicated proof by contradiction or this, that and the other, right? So did everyone follow this? This is something that you can convince yourself by just taking a few examples that this inequality is going to be this way. Okay. So we've got that it's a concave function. What is the next thing that we have to prove? What is the second thing? The domain of D is convex. Okay. So again, let's go back to the definition of. So this is definition of. This is convexity of not of a function, but what? Of a set. Right? This is, so if I give you some region like this, is this a convex set? No, because there is some convex combination of 2 points which does not lie in the set, right? So if I take a line like this, from here to here, all of these points over here are, from here to here, are outside. So this is not a convex set, right? So we have to use, so if I were to define it, when do I say that a set is convex? I would say if lambda 1 belongs to D and lambda 2 also belongs to D, then what should hold true? Convex combination of this, so alpha lambda 1 plus 1 minus alpha lambda 2 must also belong to D. Right? This is the definition of convexity which we want to prove. Okay. So let's go to prove it. We will, using the fact that Q is concave, which we just proved. So if I take Q of alpha lambda 1 plus 1 minus alpha lambda 2, this should be greater than, right, or equal to, I am using the property of concavity, alpha times Q of lambda 1 plus 1 minus alpha times Q of lambda 2, right. Now we are saying that lambda 1 is in D, we are saying lambda 2 is in D, right. So we are saying that lambda 1 belongs to D. What is the meaning of lambda 1 belongs to D? Operationally, what does it mean? Just go back to the definition of the domain of Du. When do I say that lambda is in D? What should happen? Q of lambda should not blow up. It should be greater than minus infinity. So if I say that lambda 1 belongs to this set, what does it imply? What does it say for Q of lambda 1? Simply greater than minus infinity. Okay, in words it doesn't blow up. Similarly, if lambda 2 belongs to this, it implies that Q of lambda 2 also does not blow up, right? So now if I take these two facts and plug it into this, what can I say about Q of alpha lambda 1 plus 1 minus alpha lambda 2? This is going to be greater than minus infinity. And this is all that I need to say that the convex combination 1 minus alpha lambda 2, therefore this also belongs to D. Right? So therefore D is a convex set. So did everyone follow this very simple logic? We use the previous fact that the function is concave. Concave means that the function value is above the convex combination of the function values, and that's it. If lambda 1 is in D, if lambda 2 is in D, then put together this implies that their convex combination also is in D. Means it's a finite number. So, okay, so what that means, it's a finite number. For example, if I ask you what is log x at 0, so it's not a number, right? So if Q of lambda, supposing Q of lambda were equal to log of lambda, let us say in some problem. So in this case, what is the domain of Q? So in this case, the domain would be the open interval 0 to infinity, because 0 is not allowed. At 0, Q blows up, so it's excluded from the domain, but any positive quantity is fine, right? So that is the meaning of saying that those lambda for which Q of lambda is greater than minus infinity. It's a funny way of saying it, but it's shorter way than saying a finite number or whatever. Okay. Fine. So what is the, I mean, I've already said this before, but what is the implication? Implication is that the primal problem can be anything. By anything I mean convex, non-convex. But the dual problem always convex. Okay. So that's a very useful fact to know. In fact, previously we had taken an example, right? When we saw that we took some simple example, we saw that the primal approach gave us one solution, we saw the dual approach gave us the same solution. So if the primal problem is difficult to solve, I can formulate its dual, and if I can solve it, I have a second way of arriving at the solution. So that's the power of it. So there is something I want to mention at this point which we will not cover in the course, but is extremely useful, particularly for those of you who will go into numerical applications of optimization. There is a tool called CVX. Who has heard of CVX? Okay, fair number of people have heard of. So CVX is it's a tool built by a bunch of people at Stanford. It's a MATLAB toolbox available for convex optimization. Okay, so in that the way we speak in words is almost how you can specify the problem in that. Minimize, so you define f, then you say minimize f subject to x greater than blah, or g of x greater than something, right? So the way we speak in words, you can specify a convex problem in it. Okay, and so it means that given any optimization problem, whether or not you can solve the primal problem, you can always solve the dual problem using tools like this. And like CVX, there are other tools, but CVX is the most popular tool. Okay, but keep in mind that CVX is extremely slow. So once you know that something is working, it's always better to move to your own code implementation of it, right? But for example, for your course project, if your problem happens to be convex and you want to do some programming, CVX is a very convenient tool to use. Just install in MATLAB and you're good to go. Okay, it's also there for Python, I believe. Okay, so that was a slight detour into CVX. Any questions on this? Okay, we are coming right to that. So his question is that if the problem is not convex, then what is the meaning of the solution to the dual problem? Does it hold any meaning for the solution of the primal problem? Okay, so that's exactly what I'm going to talk about next.